It wasn't supposed to be pressure. No. Okay. Anyway, we were very honored to have Kyunghyun Cho speak today. He's an associate professor of computer science and data science at New York University and a CIFAR fellow of learning in machines and brains. He was a research scientist at Facebook AI Research, and he was a postdoctoral fellow at University of Montreal under the supervision of Yashua Bengio after receiving his PhD from Aalto. He's had an impressive set of accomplishments, and many of you may know the GRU, a widely used variant of LSTM neural networks. And we're very excited to hear his talk on online hyperparameter tuning today. With that, I will pass it on to you.
Oh, well, thanks for the very generous introduction, and thanks for the invitation. In fact, I believe this is the first time I'm actually giving a talk in front of statisticians, so that makes me doubly nervous. In addition to the fact that this is really fresh out of the oven, we just submitted this paper to ICML last week, so it's been exactly a week since we finalized writing the paper, and we're still working on preparing the code and everything for putting it up on arXiv. So even if there is some rough edges, please do bear with me. I think we have some interesting thing I want to share with you all of you. This work was mainly done by Daniel Im, who's a PhD student at NYU, together with Christina Savin, who is my colleague at the Center for Data Science and also at the Department of Neuroscience. So when I think about deep learning, in particular in practice, it consists of 4 steps. First step is how we prepare the data, and then how we prepare the loss function, and how we prepare different types of the neural networks, or let's say hypothesis spaces over which I'm going to do the model selection. Once the preparation stage is done, now we go into the training stage. For each network architecture or some choice of the hyperparameters, I'm going to use a training set in order to minimize the average loss with respect to the parameters of these deep neural networks. And once this training is done for each and every hyperparameter choices or the possibilities, now we move on to a model selection phase where we're going to choose one particular neural networks based on the validation loss. Once everything is all done, then only at this point, we're going to now look at the test set or the test examples and then report how well this model that we have selected is going to generalize once it's deployed. And in particular, a lot of the emphasis is on the steps 2 and 3, and even more so on the step 2, that is, what is the right way to train a very sophisticated neural network in a scalable as well as the effective way. However, today we're going to, I'll try to look at both 2 and 3 steps, and in particular, I'm going to try to collapse them into one step. So to put ourselves in a correct context, so when I say that training, that there is a second step, I'm going to just almost exclusively refer to as trying to minimize the empirical risk using some kind of iterative optimization algorithm. And also, I'm going to assume that we are using a classifier that's going to be a deep neural networks that's going to be parameterized with a fixed dimensional parameters theta. And we're always going to use a differentiable per example loss with respect to theta, and then loss is obviously decomposed over the different examples. And we are going to include some kind of differentiable regularizer, but that's not really necessary in our case. But I'll just keep it there because that's what we always do. And then we often in practice use stochastic gradient descent, and stochastic gradient descent can be written down very, very straightforwardly as trying to change the parameter vector theta that is by the direction delta computed using the current value of theta, as well as a mini batch of training instances randomly sampled from the training set, together with a lambda that is the optimization hyperparameter. And the lambda, this optimization hyperparameter, often include learning rate as well as a regularization coefficient, but it can also include any other hyperparameters that are needed in order to define or fully specify an optimization algorithm. So in the case of using momentum, then we're going to have a momentum coefficient included in this lambda, which is a hyperparameter set. Or if you use atom, for instance, then we're going to have a bunch of those beta 1, beta 2, and other hyperparameters that you can imagine from the atom included in the lambda. But generally saying, it's a very straightforward function delta that's going to compute the gradient or stochastic gradient using the mini batch evaluated at the current parameter point using the hyperparameters lambda. Now, it turned out that when we use stochastic gradient descent, this choice of the hyperparameters in fact changes what kind of model class or what kind of hypothesis space we are searching for a solution. So that is, instead of thinking about having a different neural network architectures or whatnot, you should imagine the optimization hyperparameters such as the learning rate and so on to also define a hypothesis space over which we run this optimization procedure. And it's quite interesting because in recent years, there's been a lot of discussion about implicit regularization as well as the importance of the early stage of learning. And then all these papers are pointing to the direction that the choice of the hyperparameters in fact splits the parameter space and then chooses which partition the final solution is going to belong to. So in this talk, I'm going to almost exclusively restrict myself to talking about these optimization hyperparameters when I refer anything as hyperparameters here. Once the training is done, then we go into the model selection process or the stage. And then in model selection stage, we often approach the whole problem as a black box optimization problem. That is, we're going to run this stochastic gradient descent update procedure as many times as possible, given any particular hyperparameter set lambda. And what we do is, given that solution, we're trying to compute the validation loss. What that means is that there is some very complicated mapping going from a hyperparameter set to the corresponding validation loss. And then because this mapping can be extremely complicated and also evaluating this validation loss for each hyperparameter is very expensive, it is often approached as, it's understandably approached as black box optimization problem. And one of the most, I guess, popular or the widely used black box optimization algorithm for model selection in deep learning is grid search. Well, I gotta say it's the second most popular. So let's put it, let me just correct myself. And the idea is that we're going to look at this hyperparameter space, and then we'll impose some reasonable bounds on all those dimensions. And then we know those reasonable bounds because, essentially the deep learning has been a very, very scalable collective efforts at trying to figure out what are the good hyperparameters. So based on the past, let's say, 3 decades of research and trial and error, we know roughly a good range of the hyperparameters we should use. And then we simply use, identify a set of uniformly spaced points in this, let's say, large hyperparameter volume. And often we work in a log uniform space, but it really doesn't matter that much. And then it's very standard approach in the sense that it's implemented in scikit-learn. So according to the scikit-learn's manual page, it's going to try all those points in this grid and then pick the one with the best the lowest validation loss. As you can imagine, it really does not scale well with the number of hyperparameters as the number of the points in the grid grows exponentially with respect to the number of hyperparameters. So it turned out, in fact, in 2012, James Bergström and Joshua Bengio wrote a very nice JMR paper with a quite an interesting, or in hindsight, very simple observation that when you're working with many hyperparameters, what you don't want is grid search, and what you want is in fact just a random search. So what they proposed and then showed the effectiveness of was to simply select a random set of hyperparameters drawn uniformly from the space of hyperparameter or the hyperparameter volume, and then evaluate each one of them, and then pick the one that has the lowest validation loss. And as they mentioned, compared to pure grid search, they found that the random search over the same domain is able to find models that are as good or better within a small fraction of the computational time. And then this is true. And then this is one of the reasons why this random search is in fact the most popular and widely used hyperparameter optimization algorithm to this date. Now, of course, random search seems a bit too dumb. So it feels like we can do better based on what we know about optimization. So one of the, let's say, increasingly more popular approach to model selection or hyperparameter optimization is the sequential model-based optimization. And I'm talking to you, I'm talking to all of you at the Department of Statistics, so you all must know better about it. But it was a procedure that was proposed in 1998 by Jones et al., and it was published in Journal of Global Optimization. The idea is to start with a random subset of hyperparameters, but then based on the evaluation of those random hyperparameters, we're going to fit a model to this underlying black box function. And based on this fitted model, we draw the next set of hyperparameters according to some acquisition function that's going to be defined or is computed over this fitted model. And then we repeat this procedure of drawing more hyperparameters and then fitting a better model to the underlying black box function, and on and on. And then at the end of these repetitions, we're going to end up with a very good model of the mapping from the hyperparameters to the validation loss function. And then the problem all boils down to trying to find the hyperparameter set that's going to minimize this final model. This looks relatively straightforward, except that there are actually a lot of things that needs to be decided. So that is, what is the right way to fit this model? And also, what is the right way to compute the acquisition function? And these choices really do matter, because what we want is that we want this black box optimization algorithm to scale with the number of hyperparameters. And then when you think about these deep neural networks, there are tens, if not hundreds, of the hyperparameters that need to be tuned each time we train a neural network. So this has become quite popular among the machine learning and in particular deep learning researchers when the Jasper, Snoke, and others proposed to use Bayesian optimization with Gaussian process for hyperparameter tuning in 2015. And then the use of the Gaussian process has become more or less standard. However, the choice of the kernel is always tricky part, and then the choice of the acquisition function is still a actively, I wouldn't even call it a studied, but debated, let's say, topics. However, it's become one of the standard approaches to hyperparameter tuning, nevertheless, and it's implemented in scikit-optimize and can be used with the scikit-learn. So anything that is implemented and can be used with the scikit-learn, you can think of it as a standard practice. And then it actually does work pretty well, except that it is often less computationally efficient than the random search, just because of the necessity of the sequential processing of this Bayesian optimization. So while all these, let's say, approaches to hyperparameter optimization was done in the context of black box optimization, some people started to notice that, well, hold on, we know how to solve a very complicated optimization problem of training a neural network using a gradient-based iterative optimization. So why wouldn't we want to use the same kind of approach that is gradient-based optimization to hyperparameter tuning as well? So if you think about it, now we start merging the step 2 and step 3, that is a training and model selection, into a one bi-level optimization problem. We have the outer optimization, that is the hyperparameter tuning. And then this outer optimization's objective function is defined with respect to the result from the inner optimization procedure problem, which corresponds to training a neural network. So what we want to do is effectively to solve the outer optimization problem that requires us to solve the inner optimization problem. And then at the end of the day, it's just a one big optimization problem that we need to solve. So in practice for deep learning, this bi-level optimization, in fact, can be collapsed into just a single optimization procedure. So let's imagine what we do in the inner optimization step. In the inner optimization step, what we do is to solve the problem with SGD with a finite compute budget. That is, we are allowed to take, let's say, capital T many steps of SGD, starting from some initial starting point. And then what you can imagine is that this is simply just a summation of T many terms. And once you start viewing in this angle, you notice that this sum of the stochastic gradients is differentiable with respect to the optimization hyperparameters lambda. As long as, of course, this delta function there is differentiable with respect to both theta, the parameters, as well as the lambda, the optimization hyperparameters. And you notice that in practice, all the optimization algorithms that are being used widely to train these deep neural networks are, in fact, differentiable. once we realize this, then we notice that we can in fact compute the gradient or the Jacobian of the final solution from the running SGD steps t many times with respect to the optimization hyperparameters by essentially back propagating through the back propagation steps. And then this was actually proposed. Oh, okay, so there is a typo. It's not 2020, but 2000. So Yoshua Bengio wrote a paper in 2000 presenting a methodology to optimize several hyperparameters based on the computation of the gradient of a model selection criterion with respect to the hyperparameters. What that means is that we're going to now collapse this outer and inner loops into one optimization problem, where the inner loop part or the solution of the inner loop is going to be simply replaced by the sum of the t many gradient or the gradient-based update steps. And then what that means is that this is now just a usual minimization problem where we are minimizing this validation loss with respect to the optimization hyperparameters. Unfortunately, it's very, very expensive, as you can imagine. And then the reason why it's expensive is because we need to compute the Hessian or the Hessian vector or the Hessian matrix multiplication over and over. In particular, if you think about what happens when we unroll the process of SGD, we do have the gradient that is added to the previous time steps parameter in order to get the next steps parameters. And if you're trying to compute the Jacobian of this whole process, then we Jacobian of the next parameters given the earlier parameters or the one step before, then we end up with the identity matrix plus the Hessian of the validation loss with respect to the parameters. And then that one can be pretty large, in particular in deep neural networks. So when we build a deep neural networks, we get easily millions, if not hundreds of millions parameters. And then I don't know if you've been following the latest GPT-3 from OpenAI, which is one gigantic neural network, has 1 trillion parameters, or was it 175 billion parameters? But at that level, the order of magnitude doesn't really matter. It's just gigantic. And then computing the Hessian or the Hessian vector product is just very, very difficult. And in this case of the gradient-based hyperparameter optimization, we have to do it over and over and over and over and over and over in order to compute the gradient and find a good hyperparameters ultimately. What that means is that we need some kind of approximation, and then that approximation should enable or allow us to make an appropriate trade-off between the, let's say, the computational tractability and the quality of the hyperparameter estimation. And of course, I'm not the first one who's talking about this. Already in 2000, Yoshua pointed out these issues of gradient-based hyperparameter optimizations. And then ever since 2015 or so, a lot of people have been trying to solve this problem by coming up with some ways to approximate this computation of so-called hypergradient by, for instance, truncating the inner optimization trajectory, or you relying on the implicit function theorem, which is going to be roughly similar to the truncated backprop through backprop, or even trying to use an optimization algorithm that is reversible so as to minimize the memory use that is often growing really rapidly if we wanted to compute the backpropagation through backpropagation of any kind of optimization. And there are a lot of such efforts. So this is a really nice table from Lorraine 2020. And then in this table, they have just essentially enumerated all the approaches that have been proposed in order to solve this computation of the hypergradient or solve this gradient-based hyperparameter optimization with some kind of approximation. Of course, there are exact ways to do so, but those tend to be kind of impossible. And then there are some ways in which you can solve the problem very, very well, except that they are going to require a lot of computation, meaning that we cannot really solve the problem of hyperparameter optimization in an online manner, that is during the training, but only can work in an offline manner. And then that one has a very limited applicability in a sense that that kind of approaches cannot address the dynamically adapting the hyperparameters during training. And then, as you can see, there are so many different ways to do so. In fact, if you look at the very last row, there is a Bayesian optimization, but one above that, there's something called hyper network. And then that's kind of, let's say, as like the deep learning community's way of solving any problem. That is, in order to find the good hyperparameters for training a deep neural network, we are going to train yet another neural network that's going to predict the good set of hyperparameters. However, as you can see, that actually does involve having to find yet another set of hyperparameters. So that's not really what we want to do. So this is so far what people have been doing. Now I'm going to move on to talking about what we propose to do here. I mean, I want to say that this is like revolutionary or whatnot. And then that's what I thought about 2 years ago when Christina and I kind of came up with this idea. But looking back, it's kind of obvious idea. But hopefully, I'll be able to explain it to you in a way that's going to excite you. And then also that sounds very, very exciting. And then the first thing that we started to realize about a year and a half or so ago was that the learning is a recurrent network. And both Christina and I have been using and working with recurrent neural network for various purposes. Christina mainly to understand how to build a theoretical neuroscience models, and for me to handle variable length sequences such as language. But looking at those recurrent neural nets over and over, we started to see that these recurrent neural nets look awfully a lot like the gradient descent optimization procedure. Let's see what I mean by that. So the inner optimization part, that is the training part of deep learning, can be depicted graphically in this way. So we have a theta t-1, that is the current state of our network, or the current state of the optimization. And then given that, we have this delta function that takes as input the current state of the optimization, as well as the new input, that is the mini batch bt, based on this lambda, the optimization hyperparameter. And then whatever comes out of this delta is going to be added to the current state of the optimization to return the new state of optimization, that is theta t. And we apply this over and over until we hit the some, let's say, stopping criterion. And then the important part here is that we are applying the same process over and over and over while maintaining the memory of the state of the optimization procedure. Now then, let's talk about recurrent network. So what does recurrent network does? Recurrent network processes a sequence of inputs, which can be a stream of data or could be just a given sequence, one item at a time. And then when the new item is given to this recurrent neural network, what it's going to do is it's going to take as the input this new input, as well as the current state or the memory state of this recurrent neural network, ht-1, and then computes the new updated state of this recurrent network, that is ht. And then this update procedure, which I use the G here, is parameterized using theta. And then you probably have heard about the LSTM as well as GRU. These are widely used recurrent neural network, and then these are quite sophisticated, but they end up being just a one layer of neural network parameterized with theta. And as you can see, what I meant by learning is a recurrent network. I'll just go back and come back, come back. They look exactly the same. In fact, they are largely equivalent. That is, learning a neural network with the iterative optimization or the gradient-based iterative optimization procedure is, in fact, equivalent to building a recurrent neural network. And what that means is that the gradient-based hyperparameter tuning, that is, trying to figure out what this lambda, the optimization hyperparameters are, in order to minimize the validation loss, is equivalent to training this recurrent neural network, that is, to update the theta in order to minimize the training loss of this recurrent network. So now let's hope I'm going to hope that I have been able to in fact convince you that that is what is happening. That is, learning or the training a deep neural network is equivalent to just running the recurrent neural network, and thereby optimizing the validation loss with respect to the hyperparameters. All optimization hyperparameters is equivalent to just training a recurrent neural network. Oh, so by the way, if you have any questions, please do type in a chat, or tell me so that or just ask your questions so that I can answer it. But I'm going to assume for now that everyone is on the same boat as me. That is that believing that everything at the end of the day is just a recurrent neural network, and that if we know how to train it, then that actually solves a lot of problems. So before we continue, we need to think about how we train a recurrent network first. Oh yeah, so there is a question on chat. The question is it related to learn to learn? Yes, indeed, it is related to learn in a sense that the optimization hyperparameters, or the finding the precise setup of the optimization hyperparameter, is in some sense our way of choosing one particular optimization algorithm out of infinitely many different variants of optimization algorithms. And then our choice can be thought of as, we believe that this particular choice of optimizer is good at training another network. So it is precisely learning to learn. Yes, that's a great question. So let's go back to how we train a recurrent network. And then, we use a gradient-based learning for a recurrent network as well. And then one particular, one kind of peculiarity of the recurrent neural net is that its loss, that is, I'm going to use the term total loss, is a sum of the loss we compute at each time step, that is, for each item in this sequence, the input sequence. So I'm going to use few notations here. I'm going to use a capital F to indicate there's a recurrent neural net that consumes a sequence X and outputs a sequence Y. And then theta is going to be the parameters used to define this recurrent network. Small f, I'm going to use small f as a readout function to refer to a readout function that is given the current state of the recurrent network, what should be the output at that time step. And I'm going to use G to indicate a recurrent transition function, just like LSTM or NGRU. It's going to take as the input the previous hidden state, that is the HT minus 1, and the input at time step T, XT, and outputs a newly updated hidden state HT. And then the goal is to compute the gradient of this total loss with respect to the parameters theta of the recurrent network. It turned out that this particular setup of the recurrent neural net with the total loss computed as the sum of the loss values coming out of all those steps gives us two different ways to compute, well, not the ways, but the two different views into how we should compute this gradient. The first view is, we call it future-facing view of gradient computation. And then in this case, how we are going to write it down is to write down the gradient of the total loss as the double summation over the gradient of the per step loss with respect to the parameter theta used at time step S. So we have, this can be a bit confusing because we have these time steps, and then at every time step we use the shared parameter. You can imagine having multiple copies of these parameters for each and every step in this sequence. And then for each and every step in this sequence, we have the loss function computed in that way. So then what we need to think about is that the gradient of the total loss with respect to the shared parameter is the sum of the gradient of the per step loss function with respect to one of the per step use of the parameter. So that's going to be theta S and then LT in this particular case. So we have a double summation. But then the one thing that is interesting is that the parameters, the copy of the parameter at time step S, so how we change it, or this value itself, only influences the loss values at T that is greater than equal to S. That is the loss values, per step loss values before time step S has absolutely nothing to do with this theta S. So that's the reason why this double summation, the inner summation starts only from S and then goes all the way to capital T. And then we call it future facing because when we look at the per step gradient with respect to, when we look at the total gradient, the gradient of the total loss with respect to the use of the theta at time step S, what we need to look at is that we need to look at how the change in the parameters at step S has influenced all the future per step loss functions. So that's why we call it future facing. And then this is in fact precisely the view we often take in order to use the back propagation through time. That is, at any time point, we're going to unroll this recurrent neural network all the way into the future. And then once the sequence ends, we're going to back propagate the error signal through time. So this future facing view is the idea behind the back propagation through time. However, what that means is that we can rearrange the terms so that we can also get the past facing view of gradient computation. That is, we're going to now look at per step loss function. So the gradient of the per step loss function with respect to the shared parameter theta. And in this case, what we need to do is we need to just consider how the previous or the past use of the parameters has influenced the current time steps per step loss function. And then that's the reason why we call it a past facing view of gradient computation. It's really nothing. Both of these are equivalent. It's just a way of rearranging the terms so that in one way we see that in order to compute the gradient of this total loss with respect to the parameters, we need to, at each time step, unroll all the way to the end and then back propagate the error signal. While in this past facing view, what we are saying is that in order to compute the gradient of the total loss with respect to parameters, we just go forward, but at every time step, we're going to look at the influence of all the previous uses of the parameters on the loss function at the current time step. So exactly same thing, but these two different views, in fact, end up giving us two different algorithms to train a recurrent network. Oh, I had a really nice figure here, but I forgot to actually show you while I explained this. But it's pretty straightforward here. So there's a question on chat by Bo Tiang Zhang. How to determine T? So I'm going to assume that the capital T, the length of the sequence is given for now. However, we're going to see, in fact, in the next page that that's actually not necessary in the case of the past facing view. So in the case of the future facing view, we had to go all the way to the capital T and then back propagate the error signal back. So in that case, we need to know the capital T, or we need to somehow choose capital T according to our knowledge. However, in the case of this past facing view, in fact, we can compute the gradient of the per step loss function with respect to the shared parameter theta by only looking at all the steps up until that point. So we actually don't need to know the capital T or the length of sequence in advance. We just run it until the sequence, we run out of the sequence. Now, so this was a perfect question in the sense that this is what I'm getting at here, is that this past-facing view of gradient computation allows us to build an online learning algorithm. That is, at every time we receive a new input in this sequence, we can now compute the gradient of the loss with respect to the gradient of the new per step loss function, and thereby by summing all of them, we can now compute the gradient of the total loss received so far with respect to the current use of the parameters or the entire shared parameters. So that's possible because we don't have to unroll into the future and then backprop the error. Rather, we're going back and then trying to see what were the influences of all those applications of the parameters on this current time steps per step loss function. And then, of course, everything assumes that the theta is fixed up until now, but we're doing machine learning. What we want is to make some changes that not a lot of mathematicians are comfortable with and still make it work. So what we are going to do is, instead of waiting until the end of the sequence and make one update to the parameters, we are going to change the parameters on the fly as we receive one new token at a time. And then this is possible because we don't have to wait for the future tokens in order to unroll and then backprobe. So we can just compute the gradient, partial gradient little by little. And then every time we compute the new gradient signal, we're going to update the parameters with a very, very small learning rate. And then that's going to work. And this turned out to work pretty well. So how do we compute this efficiently? Because we don't want to keep everything in the memory and then recompute the whole thing from scratch. It turned out that it's actually relatively straightforward to come up with the efficient dynamic programming algorithm, or the recursive update formula. So we can rewrite the per step loss function with respect to the entire shared parameters as the product of the so-called immediate credit. That is that what is the gradient of the per step loss function with respect to the current hidden state HT only, and the Jacobian of the current hidden state and the entire parameters theta. Now the second term tells us about what kind of influences has been propagated all the way to HT. And then this second term, which I'm going to use a capital M to denote, so this MT can be written down as the M bar T, which tells us about how the current use of the parameters influence the HT, plus the JT, that is the temporal Jacobian of the recurrent neural net, times the MT minus 1, that is that the influence we accumulated up until T minus 1 step. That is now MT equals M bar T plus JT times MT minus 1. And once we compute this, all we need to do is, so that is we update this MT and then multiply with this immediate credit CT, and then we get the temporal, the gradient of the per step loss with respect to the parameters at time step T. Now, this is a kind of a very relatively straightforward, but very confusing way of rewriting how we compute all this gradient. My suggestion is to look into our recent paper at JMRR, where we review all these, let's say, real-time recurrent learning and variance, and was authored by the PhD student of Christina Owen Marshall. And then there we have put really a careful derivation of the whole thing. So if you're interested in it, you can take a look at the paper. But I won't be able to go into too much of a detail today. So the overall procedure, which we now call as the real-time recurrent learning, was proposed, or not really proposed, because this is just a way of rearranging the terms to compute the gradient in the past-facing manner, was studied, let's put it like that, for very extensively for the first time in 1989 by Williams and Zipser. And it's relatively straightforward. These three steps are the only thing that is needed in order to implement this. So we first update the influence matrix. We compute the immediate credit by looking at the loss function at time step T, and then update the parameter by the product of this immediate influence and this influence matrix. And then we just do it every time we receive a new input. Unfortunately, it has not been, I gotta say that it is not being widely used in practice because it's actually quite expensive. The memory complexity is cubic to the number of the neurons in the recurrent neural network. The reason being that it is quite natural to imagine the number of parameters being the square of the number of units in a network, because of the, if imagine a fully connected layer for two layers with the 1,000 neurons, we're going to have 1,000 by 1,000 way matrix. That's going to be 1,000,000 of them. And then that actually leads to the influence matrix M of the size that is n times the n squared. So the memory complexity alone is cubic, which makes it really, really difficult to use with the modern day neural network, where the number of the units is pretty large and number of parameters is even larger. But then, of course, we started to ask the question, wait, hold on. This is expensive indeed. Cubic complexity is never a good idea. But what if the number of parameters in a recurrent neural net could be O1, that is constant, and then has nothing to do with the number of neurons in this network? Then suddenly it's kind of usable because the memory complexity becomes ON, and then that's the usual memory complexity we need anyway for any kind of backpropagation based learning. That's where we finally get to this online hyperparameter tuning. So I had to give all those as a necessary background. And finally, I'm going to tell you how we are going to use all these ideas in order to derive an online parameter tuning algorithm. But it turned out that having this background in the proper context, which hopefully I've been able to do so, makes it so trivial to build an online hyperparameter tuning algorithm. So all we are going to do is apply real-time recurrent learning to hyperparameter tuning. And that's just very trivial application of RTRL, because we already know that SGD-based learning of a deep neural network is nothing but a recurrent network where the network parameters serve as the recurrent net's hidden state, and the optimization hyperparameters serve as the parameters of this recurrent network. And then what I showed you, what I'm showing you on the screen at the moment is precise copy of the RTRL's update. Let's just go back to see how it's saying. So let's look at this. Let's rearrange terms parts. So look at the first bullet point, second bullet point. We have the immediate credit C, we have the influence matrix M, and then we have the recursive formula in order to compute the influence matrix M at time step T. Let's come back. And then what you see here is precisely those two equations. And the only thing that I have replaced was to replace the theta with the lambda, because now lambda is the parameters of this learning as a recurrent neural net idea, the network. And then I have replaced the HT with theta t, because the hidden state in recurrent neural net is precisely state of the optimization, which is the network parameter. And then everything else is exactly the same. Now, of course, it looks pretty trivial, but it's not at all trivial, because computing this recursive update, or the updating the influence matrix, is quite expensive due to this Hessian that we need to compute. And in this case, this Hessian involves, this Hessian matrix itself is going to be the square of the number of parameters, the size of this Hessian matrix. But it turned out that, like the simple stochastic approximation to the Hessian vector, or the Hessian matrix product, some people call it Permuter's trick, or I just call it stochastic finite difference, works very, very well in this particular case. If you're interested in some of the intuition behind this, Domke wrote a really nice blog post. It's short and still has all those kind of the same intuition behind it. So I highly recommend you to take a look at it. And suddenly, and then let's say you believe that believe me in that we can use this kind of cheap stochastic approximation to computing the Hessian vector product, and then it's even going to be unbiased. Then the whole use of the RTRL is now computationally feasible, unlike when we try to use the RTRL to train a usual recurrent neural net, because the size of this influence matrix M, which was a problematic one, so that one had the n cubic number of elements in the RTRL for training a recurrent neural network, suddenly has, in fact, the ON number of elements within it. Because now what we often do in practice is to make a neural network an optimization procedure, or to choose the optimization procedure, so that the number of hyperparameters, so the size of the lambda set, is going to be substantially smaller than the number of the actual parameters. So even if we have a square of the number of hyperparameters, still not going to be too big of an issue. Yes. And the interesting thing is that we can further lower this computation or the memory complexity by using some of the computationally cheaper unbiased approximations out there that have been proposed in recent years. And then one of my favorite one is the URL Unbiased Online Recurrent Optimization by Telek and Olivier from 2017. And again, if you're interested in these cheaper alternatives to the RTRL or the cheaper approximation to RTRL, please do take a look at the Marshall 2020, where we have essentially enumerated all these computationally more tractable, often unbiased, but sometimes biased approximations to RTRL. So we haven't really explored using this for our current work, but I think this might be a way to dramatically scale up the possible number of the hyperparameters in the future. And then that's it. In fact, it's this straightforward. We follow the RTRL as it is for hyperparameter tuning, and then suddenly we can update the hyperparameters of the neural net training without having to roll out and see what happens. That is, we can really update the hyperparameters on the fly without having to wait for the entire training to be done and see what kind of validation loss it led to. So these are the two major properties of this RTRL for hyperparameter tuning. One is that it's fully online. We really can and should update the network parameters theta and the optimization hyperparameters lambda simultaneously. So we don't wait for the theta to converge to theta head or anything like that. We just really update theta and lambda together. And then the second property is that it's almost exact, assuming that we use a very small or the small enough meta learning, let's say eta lambda, it's almost exact. It's as exact as the usual approach based on the back propagation through time. So of course the question is, how well it works. Just from the mathematical perspective, it should just work as well as how well we would expect RTRL to work, or how well we would expect any other hyperparameter optimization to work, because it's just a different combination or a very interesting combination of the choice of the optimization algorithm or the hyperparameter optimization algorithm. And then this algorithm is based on the optimization algorithm that has been shown to work well on a other type of any kind of learning algorithms. So it should, but of course that's not what always happens. So we did some relatively extensive experimentation, and then let me show you, how well it works in practice. So we tried two different data sets, MNIST and CFAR10. These are very, very small, tiny data sets, but we wanted to choose a smaller data set in order to be very exhaustive and extensive about our experimentation. And then we use a 4-layer fully connected, it's a fully connected neural network with the 4 hidden layers for MNIST, and we use ResNet 18 from the Kyunghyun's paper from 2017 for CFAR10 dataset. We use the Atom as the optimizer, and then Atom has number of optimization hyperparameters, including the initial learning rate, I think the beta 1, beta 2, all these weird momentum terms, and a few others. And then we always use the weight decay together in order to see if we can indeed learn or adapt the weight decay regularization coefficient in addition to the optimization hyperparameters. So first, does it work better than or as well as the black box optimization approaches, such as a Bayesian optimization as well as a random search? So on this slide, I'm showing you our experiments run on CFAR10, and we compared it against the random search as well as Bayesian optimization using the scikit optimized toolkit. And we have tried actually various optimization algorithms in addition to Atom. So we tried to use just a fixed learning rate SGD. We tried to use a SGD with the varying learning rate scheduling, where the scheduler has some hyperparameters. And then as you can see, and then we ran everything until we found one network that has the target test loss that is not used for any of them to be below 0.3. And then what we see, what you can see as well, is that the proposed approach, which I'm going to, we use the OHO as a, like the shorthand notation, so online hyperparameter optimization. We see that this one is substantially more efficient in terms of the number of trials that is needed. Well, first of all, because all we needed was just a one trial in general, one or two trial in general, and then compared to, and then this actually leads to the huge improvement in wall clock time as well, because we don't really have to go back and forth in this learning procedure. All we need to do is just update this influence matrix at each time step. And then this influence matrix is not really large because the number of the hyperparameters is so much smaller than the number of the parameters in a network. Now, of course, one of the things about this optimization or the hyperparameter optimization algorithms is that we always see that some of the algorithms work really well, but sometimes they are not really stable. So we just wanted to check how stable it is by just sampling all these initial learning rates or the initial values of the optimization hyperparameters from random distribution, and then run the trainer model many different times, with or without the proposed online hyperparameter optimization. And as you can see on the screen, it almost never fails. That is, regardless of where this hyperparameter optimization started, when the learning has ended, that is that the learning in terms of updating both the parameters as well as hyperparameters, they almost always end up with the test loss that is very tight in the variance and is very low in the actual value. So this is really good. It means that this online hyperparameter optimization really works well and is stable across the various initializations of the hyperparameters. Now, the second thing we wanted to check was the scalability. Of course, we now know that the wall clock time-wise is good, but the earlier experiments just used a single set of the optimization hyperparameters for the entire network. What if we increase the number of hyperparameters? What kind of, let's say, expectation can we have? So what we did was to give each layer, so we're going to group the consecutive layers into some number of the partitions, and then each partition is going to be assigned a separate optimizer. So we'll use the atom, of course, still, but each layer would have a different atom hyperparameter, such as the initial learning rates, as well as the weight decay coefficient. And then by doing so, we can now control the number of the hyperparameters very easily. So on the slide, you see that you see on the x-axis is number of hyperparameter sets, and then you can simply multiply that with about 3 to 5 in order to get the actual number of the hyperparameters. So in the case of MNIST, we could make a 6 different, let's say, up to 6 hyperparameter sets because we had the 4 hidden layers. Now in the case of CFAR 10, we could really make as many groups as we want. So we tried even making into a 62 hyperparameter sets. And then what we see is that the more hyperparameters with the proposed approach, the better test loss we get ultimately. And then the interesting thing is that even the variance of the final test loss decreases as we increase the number of the hyperparameters. Now, unfortunately, increasing the number of hyperparameters does imply that the wall clock time increases as well. However, this simply tells us that we can really make a fine-grained trade-off between the final performance in terms final loss and the wall clock time, which is rather an advantage rather than disadvantage. Now, of course, it's an online hyperparameter optimization. What we have in the ultimate goal we have in our mind is that this is going to allow us finally to deploy a neural network that starts from scratch and then updates itself as it receives one item at a time. And then we hope that this network will be able to adapt so well that even when the underlying input distribution or the environment is non-stationary, it will be able to quickly adapt to the changing distributions and work as well as possible along the trajectory of deployment that is equal to training. So here on the slide, what I'm showing you is that as we train a neural network, at any arbitrary time point, we're going to simply perturb the learning rate or the hyperparameters. And then After this perturbation, we check whether this online hyperparameter optimization algorithm can recover from the kind of catastrophic perturbation. And then it turned out that it really can do that really well. And within a few tens of updates, it was able to bring down. So we usually perturb it to the higher value, so that it's going to be quite ridiculous from the learning neural net learning perspective. But within, let's say, several tens or hundreds of updates, the OHO was able to recover the hyperparameters back to the normal level, and thereby also bringing down the test loss to the original level without too much of an issue. So I think there was a Roger Gross at University of Toronto who tweeted about it, saying that if anybody's going to propose a new optimization algorithm and then say that that optimization algorithm works well, then they have to make sure that the number of hyperparameters they need to tune shouldn't be as high or higher than the original algorithm they are compared against. And unfortunately, this OHO, just like any other black box optimization algorithms that have been used, do have some of the hyperparameters or the meta hyperparameters, or more like design choices that need to be made. So we just looked at some of the possible alternative design choices and see what kind of impact we see. So one is that we can decide to simply use a training set instead of the validation set for hyperparameter tuning. Now we all kind of can guess that using validation set is very important to avoid overfitting to a training set, but then wouldn't the use of the validation set lead to the overfitting in the validation loss as well? It turned out that that's actually not true. So we do see that if we use the training loss, then we clearly see that the hyperparameters are adapted to minimize the training loss, and we do observe a severe case of the overfitting, such as curve here, such as a curve here. However, when we use a validation loss to tune hyperparameters while network parameters are tuned with a training loss, what we saw was that we actually do not see any kind of behavior of the overfitting to the validation loss. So the test loss does not go up. This is an interesting observation that I believe calls for further future research. But it just shows that we should use a validation loss, and then without worrying too much about it. The second thing we wanted to know was whether we had to use the entire validation set every time, because that can be quite expensive. In particular, as our data sets grow, the validation set size also grows. And then if we have to evaluate the new hyperparameter and the new network parameter on the entire validation set every update, that's just going to be computationally infeasible. So during all the experiments, we actually have used a mini batch. So we use a random subset of the validation set to compute the validation gradient or the hyper gradient. And here we tested varying the size of the mini batch. It turned out that it's reasonably important to use a sufficiently large, let's say, validation mini batch at each time step. Although it looks like we don't have to go for a full validation set. And like the one thing that's always interesting to me is that I still have a difficult time in believing that the choice of the optimization hyperparameters matters that much, because wouldn't any kind of reasonable optimizer find some local minimum ultimately, regardless of the hyperparameters? But what we have seen in the recent couple of years is that in deep learning community is that the choice of the optimization hyperparameters really matters. And if it does, then our algorithm should be able to capture this kind of long-term dependency. So does it do that? So we decided to test it, and it turned out that it's very, very straightforward to test it. All we need to do is trying to reset this influence matrix once a while to the all zero values. That is, we're going to make this RTRL forget about the long-term influence at once a while at the frequency rate of tau. And then if the final test loss is invariant to this reset frequency, that probably means that for hyperparameter optimization, in particular the optimization hyperparameters, you don't really need the long-term dependency. You don't need to capture the long-term dependencies, and it's just at every step you decide the optimal learning rate or whatnot. It turned out that in fact, in decreasing the reset frequency, that is that we reset more often. So resetting more often indeed lead to a higher test loss. This, I believe, very validates the importance of the hyperparameters in the early stage of learning. That's the one thing that have been reported by my own group as well as many other groups in the recent years. And also it shows that the proposed online hyperparameter optimization based on the RTRL can capture and will utilize the existing long-term influence of hyperparameters on learning in general. So 3 findings, and I mean, I'm very excited by the results, but as a scientist, I guess we have to stay relatively calm and conservative. So all I'm going to say is that it looks very, very promising. So it looks like it's very efficient because we can really adapt the hyperparameters on the fly together with the network parameters. It looks very effective because we often end up finding a better test loss solutions than the offline hyperparameter tuning, which Christina and I believe suggests that there is some kind of beneficial co-evolution of network and hyperparameters. We don't have any kind of rigorous justification why this happens so, but it looks like a very interesting codependence between these 2 sets of parameters. And then it looks like this online adaptation algorithm is extremely resilient in the sense that it can recover from the adversarial perturbation to the hyperparameters very quickly and to the level that was before the perturbation. So let me just wrap up. I think that timing wise, I've almost run out of time. So I'll just give you a quick overview of how we got to this algorithm. So it all started from looking at the model selection and training as a single bi-level optimization problem. And then by using the gradient-based learning for training, we realized that in fact, this pair of stages can in fact be folded into a single optimization problem. And once we start looking at this single optimization problem, that is after collapsing these 2 stages, we realize that this looks exactly like a recurrent network. That is, gradient-based learning is a recurrent network, and then training this recurrent neural net corresponds to solving this model selection problem. And we know how to train this recurrent neural net in an online manner by using real-time recurrent learning. So what we can do is now use the real-time recurrent learning to solve the problem of hyperparameter optimization, where learning the inner loop was simply another recurrent neural network. So that was the kind of process of thought. Now that I talk about it, it's only about 2 minutes that I needed in order to get to this solution. But the hindsight is 2020, and back then it wasn't really easy to make these connections. So it's a kind of interesting way to connect different dots in the, let's say, the whole pipeline of deep learning. Of course, there are a number of things I believe need to be studied further. One is that beneficial co-evolution of the hyper and network parameters. I didn't put it there just because I'm not even sure what is the right way to describe that phenomenon. But other than that, there are 2 others that I think we should be very careful about and need to study further is the overfitting to validation loss. In our relatively small scale experiments, we did not see this phenomenon of the overfitting to validation loss. But as Benjo pointed out in his 2000 paper, as soon as we aggressively tune the hyperparameter to minimize validation loss, suddenly the validation loss that we use becomes a very optimistic version of how well these hyperparameters are going to work on the test time or in the deployment time. So we have to be careful. And then I suspect that there may be a way to quantify this and trying to minimize this kind of overfitting behavior by, for instance, drawing the validation set in a particular way. But that's just my guess hunch, and I have no the kind of, let's say, the direction that can be pursued immediately at the moment. And second thing that needs to be studied is the inexact nature of RTRL. So RTRL is as exact as backpropagation through time. However, it's still inexact because we're going to change the hyperparameters little by little. And also the parameters of the network also changes quite rapidly over time. So I suspect that the gap between the true gradient and the RTRL gradient is going to grow as we train a model. But then the question is, how can we quantify that? And then if we quantified it, is there a way to narrow that gap further? But again, this one just a hunch. I believe it's my hunch that there must be a way to do so, but it's difficult to tell whether there's really a way to do so. And also, of course, do we need to do that? That's yet another question. And then that actually concludes my talk. And thank you very much for listening to this, talk with the many rough edges. And I hopefully, it was something that makes you think about, looking at the deep learning from another perspective. Thank you.
Thank you. That was great. I have a couple of questions actually. So I'll go first, I guess. Does your method only apply to continuous valued hyperparameters like the learning rate or momentum, or could it work for discrete parameters like the number of neurons in some layer or the architectural choice like which layers to have?
Right. So you're right. So at the moment, this algorithm is directly applicable only to the continuous hyperparameters. But I believe that we could make it work for the discrete discrete hyperparameters, some of them like the number of neurons or whatnot, by using those log derivative or the reinforced technique and then wrap it with the RTRL. But I think that might actually have too high a variance to be useful. But I think that there is a way to work around the discrete variables as well.
Okay, thanks. Does anybody else have questions?
Yeah, I have a question. So that's a really fascinating talk. And I was kind of thinking on the note of overfitting to the validation loss. So given that wide local minima typically generalize well, is there a way to kind of factor that into the training? So actually look for hyperparameters that lead to maybe smooth loss surfaces, or just like look for those wide minima.
Yeah, that's a very interesting idea. Yes, indeed, you can imagine having a regularization term that's going to compute, for instance, the some norm of the Hessian or norm of the Fisher information matrix, and then trying to minimize that norm or the maximize. I think that you want to minimize the norm. So, for instance, that would be possible, and then as long as those are differentiable with respect to the hyperparameters, this algorithm will be able to actually control that. Now, and then indeed, there are a number of the papers submitted and accepted that I cleared this year, which one of which was my paper, but mine was rejected while all the other papers were accepted. But there were some studies showing that the Fisher information matrix, or the norm of the Fisher information matrix, as well as similarly the norm of the gradient, turned out to be very much related to the final generalization error, and that maybe we could actually add that in as a regularization term to explicitly control for that. Yes, that's a great idea. I just think that we just don't know yet precisely what is the correct term that we want to minimize or maximize in order to find the wider minimum. Yes.
Thank you.
Okay, so I guess I have another question. Since you're training the learning rate online, sorry, can your method be seen as a type of adaptive gradient descent? Like, how does the adaptation in your algorithm interact with adaptation in gradient descent like Atom?
Yes, so that's precisely the case. So there are two ways to look at it. One way is what I just told you today, is that we are optimizing the hyperparameters of the optimizer. Another way to do it is that think of this as coming up with a adaptive learning algorithm, learning rate scheduler that is tuned and adapted explicitly in order to minimize the validation loss. So, and then we could think about having one learning rate for every parameter and using some cheaper approximation to RTRL. And then that's actually one direction that we've been pursuing over the past couple of months. And then in that case, it becomes just like Atom, except that we are being very, very explicit about minimizing the validation loss. So in my mind, this should be a better approach than, let's say, Adam or other algorithms where we end up minimizing the training loss in overall, and then hope that the final result is going to generalize. Well, here we are being very explicit about generalization.
Okay, yeah, thanks. Are there any other questions from anybody?
My talks are usually very clear, so doesn't really lead to many questions.
And a lot of our, some of the seminar students are here, so I want to encourage the students to go ahead and ask questions too.
Oh, I see.
Okay, well, I guess like we'd like to thank the speaker then. Thank you so much. This was a very interesting talk. It was really, this is great.
Thanks
Thank
for
you.
the invitation. It was really great. And then if anybody has any question they want to talk with me about, just you can always email me.
Okay, thank you.
All right, thanks. Bye-bye.
Bye.